Right, I think we can page in the intro from last time. We have uniform cost, multipath routing, and reconfigurable data center networks. Jialong Li, who's a postdoc at MPI and got a PhD at Tsinghua in 2021, and I understand he's on the academic job market now. Yours.
Thank you, Ratu, for introducing me twice. Thank you. Today, I will talk about routing, uniform cost multipath routing for reconfigurable data center networks. This is a typical topology of a data center network. The bottom lies the servers. Above the servers, we have different levels of switches, such as tall switches. All these switches are electrical switches. However, with the emerging cloud workloads, electrical switching is limited by the low switching capacity and high power consumption. Optical switching is a promising solution to replace electrical switching, and now is gradually deployed in production data centers. Optical circuit switches are used to construct dedicated circuits among TORs. With optical switches, the topologies can be reconfigured, and we call them reconfigurable data center networks, or RDCN. We can use the following diagram to represent an RDCN. The nodes represent TORs, and the number over the edge represents a time slice, meaning when these two TORs have a circuit. RDCN can be regarded as time-varying topologies. For example, at time slice 1, we had the following topology. At time slice 2, the optical switches change the circuits, and we have a new topology. Each topology will last for one time slice, and typically, the duration is around 1 microsecond to 1 millisecond. There are many path options in RDCN. For example, in this RDCN, from TOR A to TOR B, we can use one-hop paths. We can also use two-hop paths by traversing intermediate TOR D. In this case, when a packet arrives at TOR D, it needs to wait for the circuit. That's to say, a path in RDCN can cross multiple circuits. We can also use more hops. Now the question is, how should we route traffic on such time-varying topologies? Let's revisit how we do routing in static data center topologies. We use the hop count as the cost metric and apply shortest path routing. By doing so, we have a set of paths with the same length. This is called equal cost multipathing, or ECMP, which is the de facto routing policy in static data center topologies. If we follow the same method, setting hop count as the cost metric and apply shortest path routing, we will see that the one-hop path is selected. However, this one-hop path only appears at time slice 5. This path introduces a high latency and can be tens of microseconds to tens of milliseconds. The flow completion time, or FCT, is very critical to short flows. FCT is only hundreds of nanoseconds to hundreds of microseconds. Using one-hop paths for short flows will make FCT much higher. If the latency is a concern, how about choosing a low latency path? In static topologies, people use hop count to proxy latency. However, this is not true in RDCNs. The time waiting for a circuit can be more significant. Here we define latency by using the end time slice index minus the start time slice index plus 1 and times the slice duration. It is the number of time slices a packet experiences. We need to emphasize here that the defined latency is a proxy metric to indicate how much time is required for a packet to traverse from the source TOR to the destination TOR. In this case, T star is 1, so the latency of one hop path is 5 time slice, and 2 hop paths is 2. 3 hop paths is 1 time slice. Using latency as the cost metric, we will select the 3 hop paths. Then, what's the problem here? The problem is that low latency paths have large hop counts. This will introduce high bandwidth tags, defined as the product of hop count and flow size. When large flows going through a long path, packets consume more bandwidth, the bandwidth tax is high, and the network is congested. So, what lessons can we learn here? First, the cost metric should take both hop count and latency into consideration. Second, path selection should be subjected to flow sizes. We propose a new metric called uniform cost to include impact by both latency and hop count. Uniform cost has 2 terms. The first one is the latency of a path P, and the second term is related to hop count, alpha times hop count times flow size, and divided by B. Here B is the link bandwidth, and alpha is the await factor. Determine the relative importance between latency and hop count term. How do we understand uniform cost? Uniform cost represents the price that a flow F traverses a path P and is specific to both paths and flows. And a flow should choose a path with the minimum uniform cost. Based on this new metric, we propose a new routing scheme called Uniform Cost Multipath Routing, or UCMP. We regard UCMP as an eCMP equivalent in RDCNs. Here we show an example of UCMP path selection. There are UCMP paths with hop count varying from 1 to 4, and we have 3 flows, and their sizes are 1 megabytes, 100 kbytes, and 10 kbytes. For each flow, we calculate the uniform cost and list in each column. Then we choose the minimum uniform cost and select the corresponding path. Here, flow 1 choose 1 hop path, since the flow size is large, at least in this case. Flow 2 selects 2 hop paths, and flow 3 use 4 hop paths. It is because flow 3 has small flow size, the hop count penalty is little, and latency matters more. So it chooses the path with the minimum latency. In this example, we assume UCMP paths are known in advance. Now the question is, there are so many path options in RDCNs. How to find a path with the minimum uniform cost for a given flow? Can we simply replace the old cost metric, hop count, with uniform cost and applying shortest path routing? The answer is no. The first reason is that uniform cost is associated with an entire path, not for an edge. So we cannot use shortest path routing algorithm. The second reason is that we cannot calculate a path for every flow size. Let's revisit the paths and their properties in RDCN. Here we list all possible paths between a top pair for a time slice. 1 dot represents 1 path. The x-axis is the hop count, and y is latency. For each hop count, the paths with the lowest latency are called unhop fastest paths. And the globally fastest path is the one with the minimum latency, and its hop count is Hmax. Among all these paths, given a flow F, which path may have the minimum uniform cost? In the definition of uniform cost, alpha and bandwidth B are known, flow size is given, then only latency and hop count matter here. If we fix the hop count and check the path vertically, we can see that red dots have lower latency compared to the gray dots, meaning the gray dots have higher uniform cost and will be excluded. If we check horizontally, the paths with hop count larger than Hmax are not considered. These paths have higher hop count and higher latency than the globally fastest path. Now we found the UCMP path region. Formally defined, UCMP paths are unhop fastest paths, and N is not greater than Hmax. These paths have the potential to show minimum uniform cost. Knowing the UCMP path region, we conduct offline calculation. The basic idea is calculating 1 hop fastest pass, then 2 hop fastest pass, so on and so forth, and then stop when n equals h max, which is the hop count of the globally fastest pass. One problem is that we cannot get h max in advance. The solution is we compute a loose upper bound of h max and calculate n hop fastest pass until this upper bound. Finally, by checking each pass latency and hop count, we filter out the non-UCMP pass. We skip the details of the algorithm here, and please refer to our paper. Offline pass calculation can simplify the system design, and for online assignment, it is because the minimum uniform cost pass is related to flow size and cannot be known in advance. UCMP pass information is stored at toll switches. For the online assignment, a straightforward solution is encoding the flow size into the flow package, and then selected path is encoded into package header. However, this solution is impractical. First, encoding arbitrary flow size introduces a huge overhead. Second, precise flow size may be unknown. We propose bucket design and use flow agent to solve these two concerns. The intuition of the bucket design is that a UCMP path presents minimum uniform cost to a range of flow sizes. Here we show an example of UCMP bucket calculation. There are UCMP paths with hop count and latency. Using the uniform cost equation, we calculate the flow size as a turning point between two adjacent paths. Same as the previous example, alpha is set to 1 and bandwidth is 100 gigabits per second. For 1 hop and 2 hop paths, the boundary flow size is known here. That means flows larger than this value should choose 1 hop path, and smaller flows should choose longer but lower latency paths. Follow the same method, we calculate the boundary flow size between 2 and 3 hop paths, and between 3 and 4 hop paths. These flow boundaries compose flow intervals, and we call them buckets. For example, bucket 0 represents flow size from 0 to 25 kbytes, and it maps to 4 hop paths. Then we map flow size into buckets and choose the corresponding path. Here, flow 1 falls into bucket 3, then it selects 1 hop path. This path selection is exactly the same as the one where we get by calculating the uniform cost. Flow 2 falls into bucket 2 and selects 2 hop paths. Flow 3 chooses bucket 0 and uses the 4 hop paths. According to the equation of calculating buckets, we know that at different time slices, the latency variance can lead to different buckets. So we need to combine all these buckets. The question is, how many unique buckets across an entire RDCN? Our results show that with 108 tools, there are 27 unique buckets, and the number only raised to 42 under 1K tools. We use DSCP with 6 bits, providing up to 64 buckets, which is sufficient to represent all buckets in a large-scale topology. With the bucket design, we can eliminate arbitrary flow size encoding. The uniform cost calculation can also be simplified by only checking the bucket indexed. For flow agent, we use the outgoing package to map the bucket indexed. When flows start, these flows are regarded as short flows. With more data sent out, they will gradually select the path for longer flows. Later, I will show that this design has little difference compared to the case where precise flow information is known. For the selection of alpha, we set alpha to 0 initially, then we turn alpha according to the traffic load change. When the traffic load is light and network is congested, we should increase alpha to increase the hop count penalty. Flows tend to use shorter paths and the network is less congested. When the network is light low, we can reduce alpha to make more flows use low latency paths. UCMP supports alpha live turning. We don't need to recalculate the bucket when alphas change, and we have a detailed proof in our paper. Now we go to the evaluations. Here I just simply go through some baselines. VLB uses any two hop paths, and Opera is the state-of-the-art solution. It uses a hard cutoff of 15 megabytes. Flows larger than that value will use VLB, and short flows will go to low latency paths. First, we list some UCMP path characteristics. This figure shows the distributions of the number of UCMP paths per time slice between top pairs. We can see that more than 20% of the top pairs have more than 5 paths per time slice. Then we check the entire cycle. Around 75% top pairs have more than 40 unique paths per cycle. These UCMP paths, although not many in numbers, are chosen for the purpose of minimum uniform cost. UCMP provides a wide range of high-quality paths throughout time. We need to emphasize here that UCMP is general to arbitrary RDCN circuit schedules. We observe similar results on other schedules. Then we show the hop count distribution. Compared with single-pass Opera, UCMP has 25% hop count reduction. Next, we show the FCT performance. VLB experienced high FCTs for short flows because of the long circuit waiting time. KSP experienced very high FCTs, especially for 5 paths. Opera also realized high FCTs, and 5 paths is worse than single paths. For our solution, we tried 2 different congestion control algorithms, NDP and DCTCP. With NDP, compared to single pass Opera, UCMP realized 53 to 98% FCT reduction. Opera has high hop counts, the bandwidth tax is high, and the network is congested. In contrast, for UCMP, minimizing uniform cost directs short flows to longer but lower latency paths, and long flows choose shorter paths to reduce bandwidth tax. UCMP also realized high bandwidth efficiency. We calculate the average hop count for all packets and use 1 divided this number to get bandwidth efficiency. A high bandwidth efficiency means a low bandwidth tax. UCMP realized 55% bandwidth efficiency improvement. Finally, we compare the FCT performance under precise flow size information and flow agent. We see that these 2 curves are quite close to each other. This figure proves that UCMP routing does not require precise flow size information. We also set up prototype testbed. This testbed consists of 3 terminal switches and 4 servers, emulating 4 optical circuit switches and 8 tools. UCMP still outperforms all baselines, thus verify the correctness of our simulation experiments. Let's summarize here. We propose a new metric, uniform cost, to capture the price a flow uses a specific path in RDCNs. We calculate UCMP paths offline and assign the minimum uniform cost path to flows online. Simulation and testbed results demonstrate that UCMP routing realized low FCTs and high bandwidth efficiency. And we regard UCMP as an eCMP equivalent in RDCNs. And here ends my talk. I'm happy to take questions.
Very nice work. I enjoy it. Xiaoming Fu from Göttingen, Germany. So you have a very nice pick of this uniform cost. But you define these, let's say, hop counts and flow size, as well as this, what's that, the other factor?
Hop count and latency.
Latency.
That's the 2 key points.
But you didn't consider the bandwidth. Why? So in the first place, that, okay, flow sizes somehow capture this, but it's not exactly the capacity requirement, right? So if, I mean, as a side outcome, the bandwidth use would be better, but if you consider the bandwidth use in the first place, would that make better sense?
Okay, very nice question. Okay, I think I can answer your question in 2 ways. First, do we consider bandwidth? Yes. So you can see there's a B in the equation. B is the bandwidth in the network. And the second one is, I mean, you are meaning the available bandwidth in the network, but this uniform cost is modeled in the offline mode. That's to say, we know nothing about, we don't consider the real situation about in the network. But we do, return back your question, we do consider bandwidth.
Thank you.
Over there.
Hello, thank you for a great talk. I'm Ke-Xin Liu from the Huawei computing product line, and I have two quick questions. The first is, how is your work much related to the optical switches? Because I think it can be also applied to the circular switch networks, because in the circular network, it also has some multipath to choose. And the second one is, you said that you configure the strategy of the routing offline. But you also mentioned that you adapt the alpha according to the network utilization. So how you adjust alpha online, since the network is dynamic and the network maybe have some traffic burst. Thank you.
Okay, so let me answer your second question first. So how do we change alpha online? Here I provide a simple toy example here. So initially we set alpha to 1 here, and we calculate the buckets. So now here comes the flow F with the flow size 800 kbytes. So we can see that this flow maps to the bucket corresponding to 2 hop paths. Then I want to change alpha because let's say now the network is very congested. Yeah. I want to increase the hop count penalty. So I increase alpha from 1 to 2. If I recalculate the buckets, it is in the bottom line. And this flow, you can see that it falls into the 1 hop path bucket.
People cannot see your slide. Actually, I think this is getting way too detailed maybe. So let me just step in and let's thank the speaker.
Okay, let's take it offline. Thank you.
Thank you.